Hello. Sorry, I had to put it into presentation after starting the screen recording, but um, today we're going to be talking about the simulation versus the simulation, which was observation of an object at a constant speed, versus the Python created program of this model. And so for my sphere, I just used a foam sphere from the Industrial Design Studios. And I used the tracker app, and I got over 60 points in data to graph. And I wanted to show you both my models for the Python and my uh, simulation. Oh, sorry, because uh, my Python, I really didn't change much. I changed only the starting position and the starting velocity of my ball. And then oh, sorry again. I changed the amount in which the vector increased each time on the ball position due to, of course, the velocity. And I put fnet to 0 because this is a constant speed, constant velocity problem. Fnet is going to be 0. So here are my graphs from the simulation, or not the simulation, but the tracker app. And here you have my position, which shows generally a pretty straight line. To be honest, there are a few kinks in it, but that is due to just random error and perhaps friction on the floor, which may have disrupted the net force of 0. There may have been some forces which I had not intended to get into the problem, and it is expressed in these kinks. As we look over to the velocity or the acceleration graph, you can see the same. It goes back and forth. But if you really look at it, the average is 0. And this is because when the Fnet is 0, the acceleration is going to be 0 because Fnet equals mass times acceleration. As we look at the velocity one, it's similar to the acceleration one and where it's all over. However, it does average out to be just a constant positive value if you really do look at it. As we move on, I have my graph that I created in Excel based on the observations. And you can see here that with a line of best fit, it really does look like a real, position versus time graph for a constant velocity object. And I found the average velocity to be about 0.27 meters per second. And this can be shown in the equation for the trend line in this graph. I also have off to the side a small picture of what the simulation looked like on Python, because as you see, the yellow dot is going to be the 0 x-axis marker, and the big blue dot is past that to show that it does pass the x-axis. As we move on next, we have the observation versus predicted. And the blue line is the observation, which was created through the tracker app. And the predicted was based on the Python. I gathered some points from my Python code. I tried to grab points with very small intervals in between them to ensure that this would keep the reliability of the problem and the correctness or exactness of the problem. And as you can see, these two match up almost perfectly. The slopes are very similar, and the y-intercepts are very similar. They're almost identical graphs, and this is because the observation performed exactly how I would have predicted it. And as we move on, finally, we have the questions that we were asked to discuss in the video. And the first question, my answer is, if the axes were changed such that the signs of the x-axis were flipped, the sign of the slope would be flipped as well, because if the signs of the x-axis were flipped, then it would be going in the negative x direction rather than the positive x direction. So this would just flip the slope, and as a result of this, there would still be a constant velocity. However, the constant velocity would be negative. For the next question, talking about how would you know if there were forces acting on your sphere, it would be tough to point out all the forces acting on my observational model due to the presence of potential friction, which is very minute and can't be seen by the naked eye. However, it can be seen with those kinks in the line, as I had talked about previously. However, a good example of forces that you can cancel out and assume is the natural force and the gravitational force. And this is just because the ball isn't, going into the ground and it's not floating in the air. These forces are balanced so that the sphere stays right on the ground. Thank you so much. Bye.